3.2 is dedicated to the next family that we're going to consider, and that's the family of polynomial functions. So polynomials are kind of like nice, friendly functions. So if you look at the first example here, here's an example of what a polynomial equation might look like. So you'll notice that the polynomial has whole non-negative exponents. So the exponents are friendly. That's the way I think about it. I mean, I don't have negatives because if I had like x to the -2, I'd actually have a fraction. That's not a polynomial. I don't have fractions because actually those would be roots. Those are not polynomials. So I have whole non-negative exponents. And so the exponents are friendly, so as you might have expected, the graphs are also friendly. So they're smooth, continuous curves. Nice to deal with. So actually we don't need a lot of new information to do this section. What I mean is, well, let's see what we can piece together about this polynomial. Okay, what about, some things that we already know how to find, like the Y-intercept. That's an easy one. Okay. What about the X-intercepts? So when we're thinking about polynomials, we tend to say, find the zeros, find the real zeros. Okay, that would be interchangeable with saying, find the X-intercepts. So what we're saying there is, set the whole function, the y, to 0. So now I need to factor. So let me take out the GCF. And then let me factor that trinomial. Let's see, is it -2 and +1? I think so. Okay, so my x-intercepts are -1, 0, and 2. So there it goes. So what else can I determine? Well, I guess it would be nice to know what happens on the ends of the graph. Like, does the graph go up or down? Does the graph go up or down? Excuse me, on the left and the right. So actually that's easy to determine as well. So what I'm doing there is I'm looking for the end behavior of the graph. So I'm saying, what happens on the ends? So if you look back at the function here, well, on the ends, so over here and over here, x is a huge number, huge in magnitude. It's positive or negative, but it's a big number. So if x is a huge number, x to the 5th is going to be far larger than x to the 4th and x cubed. So what's going to happen is this leading term is going to dominate. So when I'm looking for the end behavior, what I'm doing is I'm looking at the leading term, okay? So the leading term is y equals x to the 5th. So on the ends, this graph is going to look like y equals x to the 5th. Now, of course, that's only going to be helpful if I remember what the graph of y equals x to the 5th looks like. So that's a power function with an odd exponent. So remember, those look like x cubed. Okay, x cubed, x to the 5th, x to the 9th. x to the 49th. All of those look basically like x cubed, okay? Just skinnier as the exponent increases. But as far as the ends go, I know what happens here. I can say as x goes to infinity, y goes to infinity. It's here, right? As x goes to negative infinity, y goes to negative infinity. That's here. Okay, so then that means it's down on this side, up on this side. Okay, so then I mean I have to connect this end with that 0. So then the next useful piece of information would be, well, what happens at this 0? Do I cross through like so? Or do I touch and bounce off like so? Same thing over here. Do I touch and bounce off? Or do I actually cross through? So that's actually also easy to determine. The behavior near the zeros. So here's what I'm going to do. Usually we set up this little table. This makes this pretty easy. Trying to draw a straight line. Okay, let's try that. So put the 0. We're going to put, this is called the multiplicity of the 0, which we'll use to determine whether the graph crosses or touches. So I'm going to list my zeros. So what were those? They were x is -1, x is 0, and x is 2, right? Okay, so now I'm going to say, all right, I'm going to look at the factored version of the polynomial. That's here. I can even include that. I think it'd be nice to include that up here. Okay, looks like that, right? Okay, so here's what I'm doing. I'm saying near x equals -1. Where did -1 come from? It came from this factor. So near x is -1. These factors are going to be relatively irrelevant. And what I'm going to have is, I'm going to have this basic shape, okay? Okay, well, what kind of shape is an x plus 1 to the power 1? Okay, well, an x to the power 1 is a line, right? So I'm going, what happens near x equals -1? If I zoom in really close on x equals -1, what I see is I see a line. So what does a line do? It crosses through, right? So you see how if I zoomed in really close on x equals -1, I'd basically see a line? Okay, so the multiplicity is the exponent here on that factor. So the exponent on that factor is 1. So should I write something? This is the exponent on the corresponding factor. Okay, so I go, okay, something like a power 1 crosses, right? Crosses looks like a line. Should I look at some of the other zeros? So let's look now at x equals 0. That came from this factor, right? So that means if I zoomed in really close on x equals 0, these two factors would be relatively irrelevant. And what I would see is I'd see an x cubed. Okay, that looks like a cubic. So if I zoom in really close on 0, I should see a cubic shape. So I'm going to try to I'm going to try to draw this in. Okay. Maybe I'll try to do them together. It'll be easier. Okay, so this guy goes straight through like a line, whereas this one I have a cubic shape, like so. Okay, so if it's hard to show that on the graph, you can always kind of include here and just label. That way the grader can see easily what your intentions were. Okay, so the exponent on x equals 0 was 3. So we would say the multiplicity of x equals 0 is 3. Going back. Okay. And then what's left? X equals 2. This one came from here. That guy again has a power 1. Okay, so that's power 1. See, this guy crossed like a cubic, and this guy crossed like a line then. So what kind of multiplicity would we need to get a touch? We would need an even multiplicity. Okay, so we'll get to one like that. So this guy goes right on through like a line. Maybe I'll try to graph it all at once. That seems a little easier, huh? Okay, linear, cubic, and then right on through like a line. Can even erase that side there. There we go. Linear. Okay. And then I have a nice graph. So I can even make a generalization here, right? I can say odd multiplicities, like all of these were, cross, whereas even multiplicity, that's like parabolic. We'll get to one like that probably next, those touch. Okay, so what else is there we could do with this? I could tell you one other thing. So let's see, here's a little rule I can say. The maximum number of turning points a polynomial can have is its degree minus 1. So in this case, okay, I have to look at the expanded polynomial. So the degree, that's the highest exponent on the expanded, not the factored, polynomial. So in this case, that would be 5. Okay, so in this case, the maximum number of turning points my graph could have would be 4. All right, so what is a turning point? Well, that's a point where I change direction. In other words, like I'm increasing, then I'm decreasing. So see, here's a turning point. This is actually not a turning point. I'm decreasing. Here's another turning point. So this graph only has 2. Well, that doesn't violate this rule because remember this rule tells me the maximum number of turns could be 4. So I could have less, but not more. Okay, so it would be possible then that this graph has another turn up here. Let's see, then it would have 3, 4 turning points. Yes, but not another one. Okay, so in calculus, you're going to go into more detail as far as, well, how many turning points does the graph actually have? And you're also going to go into more detail as far as Well, I mean, wouldn't it be possible? Get that one. Wouldn't it be possible that, say, this goes lower and this goes higher? Yes. I mean, without calculus, I can't tell you how high and how low the peak and the valley are there. But for us in this class, we're just getting a basic idea. Is it above or below? What is the behavior near the intercepts? What is the end behavior? So in calculus, you're going to talk more about exactly how high and how low those graphs go. What else can I do? Okay, the domain of polynomials, that's easy. These are friendly, right? This one, the range looks like it extends all the way up and down. Okay, so all that information, that was pretty easy to obtain. Okay, should I look at another one? Okay, so same idea. The difference I noticed with this one right away is this one is already factored. So actually look what happens here. You see how when I plug that 0 in, I get a factor of 0. This is all multiplied by 0. Okay, so my y-intercept is 0, 0. Let me go ahead and set up this table. Let's put the real zeros. Those are the x-intercepts. Let's put their corresponding multiplicities. Let's put if the graph crosses or touches. Okay. So this guy's already factored. So if I set this to 0, I can actually read you off the intercepts, the real zeros immediately. Okay, so what are those? Let's see, looks like -3, 0. The 0 comes from this x cubed in front, right? If the x was not there, I would not have x equals 0 as a solution. Okay, the multiplicity of -3 is 1. 0 is 3, and 1 is 2. Okay, so odd power of 1 crosses, power 1 is like a line. Odd power crosses, higher odd power is a cubic. If that was like a 7 here, it would also be a cubic. Okay, any odd power higher than 1 is cubic. Here I have an even power, it actually touches. Okay, so let me put the intercepts. -3, 0, and 1. Okay, let me get the end behavior. So remember, now I'm asking what happens on the ends. So I have to look at the leading term. Okay, I probably want to move this down. Okay, now the thing is this, be careful. The leading term is not -2x cubed. Okay, because remember, the leading term is the leading term in the expanded polynomial. So that factor, -2x cubed, just happens to be the factor that's written in front. That is not actually the leading term. To get the leading term, I have to think about what the expanded polynomial would look like. Like I'd have a -2x cubed, then I'd have an x to the 1 and an x squared, right? So wouldn't the leading term actually be negative 2x to the 6th? So that's very important. So when I have a factored polynomial, I actually have to add up those exponents. Look back at this previous example. So you see how in this one, I started out with the expanded polynomial so I can see that leading term. If I would have started with the factored form, I would have had to add 3, 4, 5 to get this leading term back. Okay? So back down here. So then our leading term is negative 2x to the 6th. Okay, so an x to the 6th is an even power function. It's parabolic, except the negative in front reflects the graph down. Now the 2 is a vertical stretch, but as far as what happens with the ends, I'm not all that interested in that. I'll include it. It's part of the leading term. Okay, so as x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. Okay, so let me see what I can do as far as the graphs. I'm looking at the table as well. Cross, okay, so down, cross like a line. At 0, cross like a cubic, and then at 1, touch. There we go. So linear, cubic. Okay, it's a little hard to show that shape, so I like to label. Now, what about the maximum number of turns? So remember, generally speaking, I find the degree, subtract 1. So the degree is the exponent on the expanded polynomial. So one more time, it'd be 3, 4, 6. That matches with this, right? That's the power on the leading term. So the maximum number of turns this graph could have would be 5. Okay, now the way I've drawn it, let's see, increasing, increasing, increasing. There's 1 turn. This is not a turn. Decreasing, decreasing, here's another turn. Increasing, here's a turn. This guy has 3 turning points. Okay, so that means, yeah, it'd be possible then that there'd be another turn. There's 5 turning points. That's something you'll look at in calculus. Okay, so I just cannot exceed that 5 turns. Okay, what else? Anything else? I guess the domain for all polynomials. It's easy. What about the range? So actually for this one, I couldn't tell you, could I? Because again, without calculus, I can't tell you what that peak is. So that's kind of interesting. So I actually couldn't ask you the range of this one. Without calculus, you wouldn't be able to determine what that peak is. I could ask you for the domain, though. So all of these are, and we're just doing the same steps. So I think this is kind of an easier section. So I don't know. Let's see, I think I copied this one down wrong. Let's see. I think I wanted this one to be a 2. Okay, so there's my third polynomial. So, okay, I can start out. I don't know. I'm kind of interested in, well, at some point I'm going to have to factor this polynomial because how else am I going to get the zeros, the x-intercepts? So I notice when I have 4 terms. Okay, when I have 4 terms, I use a process called factoring by grouping. So how that works is I group the first 2 terms and I group the second 2 terms. And I say, okay, well, what can I factor out of this first group? I can factor out an x. What does that leave me with? An x squared plus 1. What can I factor out of the second group? A negative 3. Then you double check. That'd be x cubed plus x. That'd be minus 3x squared minus 3. That looks good. Okay, then you notice that you see how now you have this common factor, x squared plus 1? So what I can do now is I can actually factor that whole x squared plus 1 out front, and that'll just leave me with the x minus the 3. So think about if you were to distribute this. Then you'd have x times x squared plus 1 minus 3 times x squared plus 1. That's what we had here, right? So that's correct. Now actually look, this guy's a sum of squares. When I have a sum of squares, that's prime. It does not factor. If I had a difference of squares, that's the one that factors nicely, the one with the subtraction. Okay, but with the sum, that's actually prime. So actually I'm done factoring. Okay, anyway. So that's the factorization of the polynomial. All right, so then maybe I'll put that up here. So now I have both versions. Let me find the y-intercept. I could have done that before or after. Let's see. If I plug in 0, I'll get negative 3. Here's the y-intercept. Now let me make my table here. So the 0, the multiplicity, does the graph cross or touch? Okay, so I'm looking at the factored form here to get the zeros, right? So to get the zeros, I take that factored form and I set it equal to 0. Now remember, I'm only interested in real zeros here, the x-intercepts. So actually, all right, I see, all right, I'm going to get x equals 3. Has a multiplicity of 1. Crosses like a line. What about this factor? Well, if I set x squared plus 1 equal to 0, there are no real solutions. Okay, so this factor actually does not contribute any x-intercepts. It doesn't contribute any real zeros. So this is kind of an interesting one then, because actually the only x-intercept is at x equals 3. Okay? Because I haven't gotten the end behavior yet. So looking at the leading term, remember I look at the expanded polynomial. Okay, otherwise I'd have to add 2 plus 1. Okay, either way, it's y equals x cubed. So that's an easy one, something like that. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. Well, let me see if I can come up with a sketch then. So down, I've got to hit the y-intercept. Okay, got to cross like a line. So there's a basic idea of what that graph might look like. I didn't list the maximum number of terms anywhere. Let's see. The degree is 3, right? 3 minus 1. So this could have 2 turning points. The graph I drew has no turning point, so I don't know. I might have something up here like that, so then I'd have 2 turning points. That you'll look at in calculus. That's a cool one. Okay, write the equation of the polynomial with zeros -2, 2, and 3, degree 4, touches at x equals -2, and p of -1 equals -6. Okay, I guess another way this one could be presented would be, I guess they could have given us a graph. So that's another way they could have set up this problem. Let's see, so I'm just curious. So 0, -2, 2, 3. Okay, so let's maybe fill that in as we go. So let's see what we can come up with. So we're given the zeros. So I mean, if x equals -2 is a 0, wouldn't it have to be true that x plus 2 is a factor? If x equals +2 is a 0, wouldn't x minus 2 have to be a factor? If 3 is a 0, wouldn't x minus 3 have to be a factor? So if I write that, I've got zeros at -2, 2, and 3. Okay, so then this condition satisfied. What else does it say? It says degree 4. So far I only have a degree of 3. So this I have not dealt with yet. Let's see what else it says. It says touches at x equals -2. So remember, if the graph touches, it must have an even multiplicity, an even power on the corresponding factor. So that means the factor x plus 2 has to have an even power. Now, I mean, I could put any even power like 6, say, except that the degree is 4. So actually that would limit me. It's going to have to be a power of 2, isn't it? Because if I put a power of 2 there, then I've got a degree of 4. And the graph touches at x equals -2. Okay, so that's all looking pretty good. Only thing left then, still need to account for, is this fact. P of -1 equals -6. So that's saying if I plug -1 in, what did I do here? Let me go back. I think I may have erased. I think I erased the plus here. Okay, let me just go through one more time. And make sure everything looks okay. So let's see, I have zeros at -2. That's x plus 2. 2 factors x minus 2. 3 factors x minus 3. Degree is 2, 3, 4. Touches at x equals -2. Okay, and let me try this part again. So now I was looking at P of -1 equals -6. Okay, so what I have to do there is I have to plug -1 in. So -1 plus 2 is 1. -1 minus 2, -4. So right now I get 12. I wanted to get -6. So the thing is this, couldn't I actually have any coefficient here in front? What if I had a 5 in front? I'd still have the same zeros. I'd still have the same degree. It'd still touch at -2, right? I could have -5 in front. I could have -100. So generally speaking, I could actually have any coefficient, as long as I don't have an x in front. I could have any coefficient in front. So what I'm going to do here is this would be called fitting the coefficient. In other words, determining A. So I'm plugging that -1 in again. And what do I get? I get 12A. And then what do I know? I know that 12A has to be equal to -6. So there's my coefficient. So let me write the polynomial then. -1/2 x plus 2 squared, x minus 2, x minus 3. Okay, then should I finish graphing it? So let's see. The end behavior, I'm kind of just going through this one. You can do this pretty quickly. Leading term will be 2, 3, x to the 4th. Okay, so down, down. Let's see, at -2, the multiplicity is 2, it touches. I didn't find the y-intercept. Let's see, if I plugged 0 in there, I'd have -1/2 times 4 times -2 times -3. Let's see, that's -2 times -2, 4 times -3, is that -12? Okay, anyway, I can even just, if I don't have that information, I can even just kind of be generic. Let's do it that way. I just wanted to get a rough sketch of this one because I wanted to point something out. Let's see, so what does the graph do at 2 and 3? Crosses like a line. So something like that, something like that. Okay, so I was just going to say, I mean, another way this problem could be presented would be what they could have done is given you this graph and said write the equation of this polynomial and then labeled this one point over here as like -1, -6. Then you would have had to say, okay, here's x equals 3. So I know a factor would have to be x minus 3. I can see it crosses like a line. Same thing here. Then I'd have to say, okay, here I see touches. So then I would write my factors out. So I'd have, okay, and then I'd have to figure out what the A was. Same thing we did, right? So you could do this based on a graph. Then you plug in this point.